Welcome back to the DOTS lectures in another year, 2026. Um, so last time we were giving examples of behavior functors that you can derive using representability when applied to modules of systems. And we were doing that mostly with respect to things that were generalized Moore machines, things like uh, actual Moore machines, deterministic or non-deterministic, um, partially observable Markov decision processes in the stochastic case, ODEs in the continuous time case. And those gave rise to a variety of behavior functors, which landed in various toposis of sheaves that we can interpret as having a temporal quality. They're very time-varying sets. Um, in this lecture, I want to go through how we can also see reachability problems as representable, but the functoriality of that representability is slightly different. And so I want to go through this to capture it because it's a sort of subtle point, and this is a point at which our very abstract discussion of the representability theorem will help us because we'll need to shift the abstract setting we were working in there to accommodate this kind of functoriality. So let me say, first of all, how reachability is representable in a sort of more naive sense, and then we'll see why this does not fit in the previous way of thinking about things. Um, so uh, uh, I will describe for you a module of systems, and it's something that we've actually seen before much earlier on in the lecture series. So consider this. Consider the following module. So note that if we have um, we can consider the following double category. So the objects, the following, let me just say the following um, uh, think of the easiest way to say this. Let's consider the category of categories. The category of categories, um, it being uh, the category of models of an essentially algebraic theory, has all pushouts. And an initial object. Although pushouts are actually a bit difficult to construct because it is not sufficient to just take the pushout of the underlying graphs. You have to, in fact, take a pushout of the underlying graphs, then complete under the axioms of a category, so adding in a bunch of new arrows, and then taking a big quotient, forcing all the relations that already existed and the category axioms. So it is in fact very easy to compute them, um, easy to compute for free categories. This is because the push out of free categories, if we have a bunch of graphs, and these are both free, then the push out here is just given by the push out of the underlying graphs. And the push out of the underlying graphs is given by taking the push out of the sets, which is to say disjoint union of quotienting of both their edges and their nodes. These are, again, category theorists' directed multigraphs, reversed. So this is simply because we have this free forgetful adjunction. And as a left adjoint, F preserves all colimits. So we can consider the double category cospan cat, right? Which is a symmetric monoidal double category in the way we described earlier. And then we can restrict it on its objects to the free categories. And I'll say maybe also we want to restrict actually all the cospans. Let me describe this in a better way. F, because it preserves all finite colimits, induces a functor like this of symmetric monoidal double categories, which we'll just call F. And what we can do is we can take a double category here, which I'll just call C for now, which sits in between this, and which is characterized by having this having the same type category, and this is having the same loose category, by category, if you will. In other words, we're going to consider C a double category formed by spans of graphs but then morphisms in this direction will actually be between the free categories. So I can put F here, here, here. And these also are free. Why do that? Well, we could just work with categories, but again, it's going to be nice to just assume everything is free in here. Because we're going to look at the reachability problem in graphs. You might as well look at it in categories, but we're going to look at the reachability problems in graphs. And then we'll come back and see how we can do this in other things like Petri nets. Okay. So this is going to be our definition of the double category C, or maybe I should call it double category of cospans of graphs, or I'll call it, maybe instead of C, I'll call it G, excuse me, for graph.
Can I ask, you talked about adequate triples before. Is this like cospan for adequate triples where you've got, where you've got both classes, those free maps?
You also need to restrict the objects. Oh, I guess you restrict the objects.
Oh, right, okay.
And then you have, yeah, I think that's right. I think that's a good point. Thank you. So that's cospan in the adequate triple, which is free categories and pure maps.
And the other thing is you've drawn a span, right, rather than a cospan.
Yes, I have drawn a span rather than a cospan. Thank you. Okay. So we're going to take, yeah, this is the good way to present it. Thank you. Using our adequate triple technology. And we've seen that this forms an adequate triple because we know that we can take pushouts like that above. Okay, great. So now we get a module of systems G, and then we're going to take only maps out of the empty. So what does that mean? Well, and I'm going to restrict. I'm going to restrict it along what I'll call discrete. So this is a restriction of the Hom bimodule where disk from cospans of finite sets to G is induced by disk from finite sets to cap, which sends a set to the discrete category on that. In other words, the free category on the discrete graph on that set. And that is a free category. And this preserves pushouts. In fact, it is determined this is the free finitely co-complete category. Okay. And this functor disk is determined by sending one, the generator, on one, to what you could call the point, the walking object or the category with a single object. And it only has the identity map. Okay. So this is a module, a right module over cospans of finite sets. And as we discussed earlier, cospans of finite sets, we can think of these as bubble diagrams. And this gives us a way of talking about composing these systems by putting them in bubbles. And that's what we talked about in the earlier lecture. Forget exactly which one. Okay. So as an example of such a system, right, we would take, well, it's an example, a system is, as you can see, a pair of maps like this. Well, I could say disk I, but I'm at some point going to just forget to distinguish between finite sets and the categories that are freely generated by them. Is we have a graph, we have a finite set, and we have a marking of some places in the graph. Right? This is what a system is. And this is an interface. And so we can think of that, for example, as a system has, you know, some graph here. Right? And some of those places are marked as public. Right? So now, if we have two of these, the way we compose them is as we've been doing for a while. I'm going to stop drawing the left leg of this cospan because it doesn't affect anything. So if we have G1 and G2, I'm going to start writing it as boundary G1 like that, just to be easy. So what we first do is we disjoint union them. And now if we have some kind of cospan here, again, of finite sets, right? Which again, remember, we can imagine as some wiring. I would like that to be differently oriented. This thing here, we can imagine as a wiring diagram involving two inner boxes, which have G1 in them and G2 in them, and then some wires on them, which is the boundary of G1, some other wires here, which is the boundary of G2, and then some wires here, which is I. And then it has a cospan. So some dots in the middle, which correspond to C, and some kind of maps like this. It's not a particularly good one, but it's okay. Some map, something like this, which corresponds to a law for composing. So indeed, it's actually generally quite nice if we also make the restriction that this be injective and that these therefore be injective as well. and that this be surjective. Uh, these are my favorite ones. That is a perfectly good double category. In fact, it's actually rather nice. I don't think I talked about, oh, right, I was going to talk about this one. I don't think I talked about this, but there's a special feature of this double category that it shares with the lens double categories, making it very nice for representable functors. But I think I'll have to return that to that another time. That is not shared by the cospan one, namely that it's thin and it's quote unquote span-like, um, despite being a cospan double category or Spanish. Okay. Um, so take your pick of whether we do that or not. But if that's the case, then we can't have annoying things like this, and we can't have this is fine. Um, but we can't have you know just dots in the middle here which don't do anything. That would be awful. That's what those two restrictions forbid. Um, okay. And given that the resulting composite, right, which is uh, G1 plus G2 dot C is the push out, right? And again, if we have some graph like this, and maybe some graph like this, and maybe, we take C to be something like this, where the map here sends everything to something containing its name, to a, let me, the map sends every element to the set containing it. There. And we might have here one, two, B, something like that. Right? Then the resulting composite here would take A and 3 and overlay them like that. And that's how we can glue graphs together using this paradigm. Okay. So the reachability problem, C problem is this. Given a graph G and nodes S, E in G for start and end, does there exist a path from S to E? So a path is a sequence of edges. A path is a sequence of edges. Each of which starts where the one before it ends. Okay? This is called reachability. Lots of problems in various practical circumstances can be reduced to the reachability problem in graphs. Or, so an example of this is like, if you want to know, can I achieve a goal if that goal is expressed, if I'm expressing this in a certain, I want to move from one place to another, I want my little robot to move from one place to another, and my graph expresses locations I can be at and possible moves I can make. So the reachability problem is very obviously, can I get from one place to the other? But then also you might ask, is my is my system safe? As in, is it false that I can get from S to E if S is my starting state and E is a bad end outcome? I want to know that I can't get there because of maybe the constraints that have been put on the graph. It really depends on what the graph means. And there's a lot of different problems that can be encoded in this way. It's a very simple problem, but there you go. So my point that I want to make here is that this can be equivalently expressed as given a graph G and nodes S comma E in G. Does there exist a map? And I'll note that it's a type map from 0 to 1, which is also known as delta 1, to G, I'll write it. I'm going to write it the other way around. I have G, and now I have S and E in there, right? So I'm going to take 0 and 1. I'm going to put them here, and then I can draw this map, which I'm going to call S comma E. So 0 maps to S, and 1 maps to E. And then I have this inclusion of this into delta 1, which is 0, 1 with an arrow, which I'll call 2. Actually, I won't call it 2. I'll call it 0, 1. Okay. So the question is, does there exist a map like this? A type map in our double category G, that is to say, in cat. Well, why are these the same? Well, because the free category, so such a map, a type map in G is a map. This is a map from delta 1 to FG in cat, right? And maps out of delta 1 in cat, they pick out their functors, right? So they have to send 0 somewhere, they have to send 1 somewhere, but we've already said where those go to S and E. So they have to send this arrow somewhere. They pick out an arrow in FG here. And the arrows in the free category are paths. So this is just another way of saying the reachability problem, again, showing that it's representable, right? And now we can make a nice assumption. Let's suppose that those edges, sorry, those nodes are actually public. So they're in the boundary. In that case, we can rewrite this square like this. This is boundary G. Inclusion. And now you can see it very much is a type morphism in G, or a morphism of systems in G empty disk. Okay. So reachability is in that way evidently representable. But this is not a particularly useful representability if we use the definition of module of systems. And let me walk through why the definition of module of systems does not give us a very useful representability here. Okay? So as a corollary, we do get a functor, which is, as we might say, which we might call reachability. See, it's going to be a lax functor. And it goes from G empty disk, and it's going to go into span set 1 dash. Right? Just like all our other behavior functors. I mean, we have a single representer here, as you can see. Okay. Now, we can look at what the compositionality of this says, and it's okay. Um, I mean, this is a lax morphism of these modules of symmetric monodal double category of, well, I should say it's a lax morphism of um, modules of double categories. Um, and so it says some kind of compositionality. But if you remember from before, it's not enough to know that we have an object which represents it, this system here, representing uh, our thing. We also needed a comonoid structure on it. Remember? And that's where we run into problems. Um, as modules of double categories. Hence. But to respect symmetric monodal structure, we need the representer to be a colax morphism. Remember, this was the actual definition we needed. From 1 to, from the terminal module of systems to G, the disk, our systems theory. Right? That's how all these things started. All right. And what did that mean? Actually, I will scroll up until we find what the um, here we go. This is what it means, right? This is what it means to have a colax point, right? So right now we've given we've given this object, right? And we could think about what we could take for here, but it's not usually, as we said, it's the identity. And let's for now just think about how that would be because it doesn't even really show up in the left-hand side, and we're already going to run into problems, right? So it is a excuse me, a comonoid structure over here, right? Vertically with respect to the tensor product. Okay, let's go down. So we need at least for this, I'll write it like this. Delta 1, boundary 1, to be a comonoid with respect to the symmetric monodal structure of G, which as a cospan category we were taking to be plus. Plus. So we're dead in the water right away for a simple reason. We do need a co-unit. And the co-unit must go into empty, the monodal unit of this. And this makes me sad because you just can't map into the empty set or category. Even if we didn't do that, let's just ignore that one, right? Let's see if maybe we salvage it. Even if we didn't do that, we would need to go into the plus. The problem here ends up being of essentially the same character, namely that the category of categories is extensive. A map into here, if this is like an arrow, this is 2 arrows. It's disconnected. This is 2 points. This is 4 points. We might be able to work with that. I mean, we might. But on the left-hand side, we're totally screwed. I mean, we can either send that arrow to one half or the other, and it's not going to give us anything that resembles what we really want for the compositionality. So let me say a little bit about what we do want for compositionality. It's sort of an obvious compositionality, right? If I have a path, say, if I want to look at the reachability from here to here, and then the reachability, say, from here to here, right? I can solve the first problem, say, with a path like this. And I can solve the second problem with a path like this. And therefore, I can solve the composite problem, which goes from here to here, by composing those paths. Now, not every solution to the reachability problem of the composite is realized in that way. This example is not a particularly good example, but if I had any edges going back, you might be able to reach things. For example, if we were to glue, can I do it in this one? Uh, if I wanted to say go from 2 to 1, which I can't do, but if I glue it in an extra arrow from them, which is something that you could do with a composition pattern, then of course I could solve that problem then. It's very important to realize that in this case we're truly getting a lax behavior functor. From solutions to the components, we can derive solutions to the composites, but not necessarily is every solution of the composite so derivable. But nevertheless, we're completely failing to even get that with this format, right? So what's the solution? So the solution, don't use symmetric monoidal loose right modules. It sounds like a big problem for us because we built all this up for that. Luckily, it's not so bad because of the generality at which we proved our representability theorem. Instead, we're going to use algebras, use algebras for double operads. Because while it is not true that this is a Colac morphism of symmetric monoidal loose right modules, it is in fact a Colac morphism of algebras for double operads. And I'll describe that because the terminal double operad, morphisms out of the terminal double operad are different than morphisms out of the terminal symmetric monoidal loose right module, despite the fact that they are somehow very similar constructs. Okay, so let me give you, before we do the double version of this, let me give you the one categorical analog. Um, Symmetric monoidal dual right modules versus algebras for operads. Right? So in this case, we've just removed the double. So this is sort of like focus on the loose direction. You can't express the notion of Colacs we're using here in this way, right? And we can't do our representability theorem, but it will get at the fundamental difference between these two enough for our purposes and give a good introduction to what it means to be an algebra for an operad. An algebra for a double operad is just that, but double in a sort of in the exact same way that a double category is just a category, but double. As in, it's an operad internal to categories. Just as a double category is a category internal to categories. Okay. So, and by operad, I always mean in a Lurie-Pilled style, a multi-category, which I will describe now. So def, an operad. An operad is a mathematical structure consisting of, one, a set of objects, which we'll think of as interfaces, and two, for any list of objects, maybe I should say finite set of objects, but finite set of indices labeled in objects. But for any list of objects, A1 dot 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 AN and B, so an operad, let's say I, in I a set of sometimes known as ops or multimorphisms or morphisms I A1 dot 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 AN come B. Oh, and they're always going to be symmetric for me. So we'll come to. Together with actions of the symmetric group, essentially saying that although I did write them as an ordered list, I don't care about the ordering. And uh, in string diagram notation, we might draw this like this. The string diagram notation is actually quite nice for keeping your head on straight when it comes to this without going crazy with indices. So now 3, we have composition laws. Oh, well, hold on. I'm not done yet. Identities. By the way, these actions have to be, they have to have the evident laws regarding composition and identities. So like the action induced by the identity is the identity, the action induced by the composite is the composite of the actions, etc. Okay. The identities, and then 4, a multi-composition. So i.e. Uh, of this form. Maybe I should have, how would I call this M? M1, and this is going to be MN. Okay. So there's a map out of this giant thing, this giant product, into the the flattening of these lists here. And what this does is it composes a bunch of things at once. So in string diagram terms, we take a thing like this with all the ANs, and then we take a bunch of things in here. Oh boy. It's getting worse. And we sort of wire them in. And then these have a bunch here. And then you imagine yourself being able to box the whole thing in to one giant triangle. And as you can see, it comes from all the C's, and the A's are cut out. Okay. And then this has to be associative and unital in the quote unquote obvious way. Uh, with string diagrams, that's not so bad, um, if you want. What it means is that another way to see this is that for any tree, right? Not necessarily planar because these are symmetric, right? I'm allowed to cross wires. Um, for any tree, there is an operation which flattens it into the single branching that you would get by looking at only its leaves and its root, which is what you can see sort of happening here. And the law is that the composite of any of if you take a single tree and at every one of its branchings you put in an entire tree, then the result of composing each one of those and then doing the final one is the same as grafting them all in and taking the total composite. Um, Again, this is sort of a nightmare to write out in full, but there's perhaps other easier ways for me to describe this, which I can. Like symmetric ones is a little fiddly, but actually, by the time you're doing symmetric operads, you might as well just do double operads, um, in my opinion. So maybe I'll tell you, maybe I'll actually tell you that because it's a pretty reasonable definition of a double operad. Okay, cool. So plus laws. Okay. So how do these things compare to symmetric monoidal categories? So, oh, and a morphism, right? I hope you imagine is a function on objects, and then for every list, a function on morphisms that is functorial with respect to both these actions of the symmetric group and these composition laws. Okay, so that's it. And so an algebra for I is an A, or fancy I, is is something called A, which consists of an assignment A of X for every X, or maybe A of non-fancy I. Am I gonna brave it? For every I in fancy I. And functions, actions. As you can see, this looks a lot like a right module. So like A is very much like what the rules you would get if you put nothing in the back and then just looked at things here, which is a perfectly valid allowance here, by the way. You can have an empty list. It does not have to be a list with elements in. Okay. This is known as an algebra. So you can see that we get algebras of systems in much the same way we've been getting these modules. In fact, the idea is very similar. In fact, this idea is actually closer in a lot of ways to what we've been talking about because when we talk about, well, so when we're thinking about the operads of interfaces, we will think about these sets here as being composed of composition laws, coupling laws. And now you can see that we actually do have separately separated out all the different inner interfaces that we're going to use. That's the main difference. Okay. So a theorem is that algebras for I correspond to operad functors from I to set, where this is the operad of multivariable functions, i.e., the objects are sets and set A1 dot 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 AN to B is just equal to the set of multivariable functions, which equivalently is set the product over I, AI into B of functions. And the composition, this composition, which looked rather complicated up here, just is plugging a bunch of functions into each argument, right? So an object f in here is a function a1 dot 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 an maps to f of a1 dot 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 an. And the composition up there is substituting in all the AIs for G's that depend on a list of C's. They're on a list of C's. Okay. And so why is that? Well, as you can see, we can understand this is an assignment of objects. And then to see this as a instead of having this on this side, we could curry this and move this onto this side and see it as a function from this into the set of functions from all the AIs, the product of the AIs into AJ. And that's exactly what the HOM is here. So we get these families of HOMs. And I didn't say it, of course, but there are laws. And the laws are associativity and unity, that the ones that you would expect if you were considering the HOM like this, which is generally the case for like what modules look like in generalized category theory. Okay, so and there's also another theorem, which is that there's in fact a an adjunction between symmetric monodal categories and operads. Um, is that the way I want it? No. Wait. Yes. Yes, it is. So to see this, right, we should note that let me talk about what U is. So U of symmetric monodal category is going to be an operad with the same objects as C, and with U of C of C1 dot 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 Cn to D defined equal to be C of C1 tensor dot 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 tensor Cn into D. And with composition using the functoriality of tensor product. Okay. Meanwhile, f of I is going to be a little more interesting. We're going to take its objects are lists of objects in I, or it's a little nicer to use finite sets labeled in objects in I, but I'm not going to belabor this too much. List of objects in I, and f of I from one list to another list right, is going to be simply a bunch of maps um, between these. So what we're going to do is we're going to partition. So it's going to be, I'm writing it here, we're going to partition the i's into some number k, right? And then we're going to take the product over all I and k of our operad I from A, let me call it like, let me write it like this. Vec A sub P inverse of I into B.
So that K being
Should I? Yes, it should be an M. Thank you. It doesn't have to be hold on a second. This would be surjective. Doesn't have to be surjective.
Yeah.
It's a map, isn't it? Yeah, that's better. Into BI. All right, so what does this arcane script mean? What it means is that we look at each one of these, right? And we pick some A's to map into it. And then we take a map, a map here is in fact a tuple of maps into each BI for some breakdown of the domain list. And the tensor product is concatenation of lists. And the unit is empty list. Okay. So, putting these together, an algebra for an operad I is also, oh, it's a lax monoidal functor. Let's look at the functoriality of this before I do any more. Right? It's actually, yeah, it's worth noting that why do we end up getting lax monoidal? This is actually a very important point here. A morphism of operads gives rise to, is it a free thing for lax? I actually think that the free one, um, let me, sorry, let me, the free one just goes into symmetric monodal functors. Um, if we have a functoriality here, we just functor it through everything. It's not lax monoidal. But, so note, a operad morphism UC1 to UC2 corresponds to a lax symmetric monodal functor. And the reason for that is that what an operad morphism is, it goes from UC1 of, let's say, C1 dot 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 CN D to UC2 of FC1 dot 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 F CN D, F of D. But what these are is by definition C1 of C1 tensor dot 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 tensor CN D, and this is C2 FC1 tensor dot 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 tensor FC2 D F of D. Right? And so note that it's not f of C1 dot 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 Cn, which is what you'd expect from a functor. And in particular, there's some special maps in UC1 that come from the identities, but aren't the identities in the operad. Namely, if we consider C1 of C1 tensor dot 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 tensor C1 comma C1 n C1 tensor dot dot dot. How about I just do two, a pair? I'll just do two of them. C1 C2 C1 C2. We have the identity in here. But by definition, this is what U of C1 comma C2 semicolon C1 tensor C2 is. So the identity actually lives up here as well. Now, it also lives in the unary one, and that would actually correspond to the identity. But when it lives up here, it can't be the identity because it doesn't have the right type signature for the identity. So if we map that over, right, f, that goes to C2 of f of C1 tensor f of C2 into f of C1 tensor C2. So f of id lives here, right? And that, as you can see, we could define to be mu of f, the laxator. Or I believe I was calling it f bar before, maybe. And it's an exercise, but a very nice exercise to run through why this, oh, and this and the corresponding empty one uh, is um, so I guess I didn't say it, but right, the C1 empty into one by definition, when you interpret the empty list, you take the tensor over the empty list and you interpret that as one. So again, id1 lives in here, and that will map over to give you, again, here, it's f, in here it's just one, again, because it's empty up top, right? Empty, f of one. So this gets here, it gets interpreted as one, C2, into f of one. And this, you see, so f of id1 gets interpreted as our uniter. And you can check that by functoriality and all the other things you get actually a Lax-Monodal structure. So, right, symmetric monodal, right, modules of categories, of symmetric monodal categories, right? These, right, M of C, these correspond to lax monodal functors from C to set. And that corresponds to operad morphisms from UC to USET, which, by the way, is just set, the operad, as I defined it. If you think about this definition is just that where the tensor product is product. And so that corresponds to algebras of UC. And now you can see that you see this definition here, where we take a list of things and we take their tensor product and then we take unaries. That's how we've actually been doing all of our compositionality before. We took a bunch of things, we took their tensor, and then we looked at a unary map out of it. And that's what we've just been doing. So in some sense, we've always been using this trick. And the reason is just because it's easier to work with symmetric monodal double categories in a certain sense because they sort of have a well-established theory and stuff. But now we can see that that this is great, right? But we can see that there's actually that now we can go back to the double world. So like, let's go back to double world.
Sorry, this is what thing. So
Yep.
lax monodal functors, these are like symmetric, lax monodal.
Yes, so the symmetric is also there, and I haven't been talking about it, but symmetry comes from the interaction with these symmetry actions of that reorganize them. And in order to the reorganizations here on UC, I should probably tell you how they work. Right, on UC, we have for sigma in aught n, we need something of the form C1 tensor dot 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 tensor Cn D is isomorphic to C sigma 1 tensor dot 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 tensor C sigma n D. And what we do is we compose by the symmetry C1 tensor dot 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 tensor Cn isomorphic C sigma 1 dot 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 tensor, tensor C, sigma n, induced by the symmetries. And there's a unique one, um, in some sense of unique, um, that can be expressible as a composite of the actual binary symmetrizer, according to the axioms of a symmetrical nodal category. Right? Like no matter which way. I mean, if you like, here's the algorithm, right? You take your sigma and you express it as a composite of transpositions. And then each transposition, you have an elementary symmetrizer. Thanks to an enormous number of reassociations and symmetrizers, you can therefore express the composite in that way. And by the coherence theorem, you're guaranteed that any two of those choices will yield the same answer. It's a bit involved. Depending on how you present your symmetric monodal categories, this becomes easier or harder. For example, there's a rather nice presentation of symmetric monodal categories. This idea, this approach to doing this, I think, is due to Koch and Haugsing, but you can express symmetric monodal categories as symmetric monodal objects in cat, understand those to be certain functors out of the category of finite sets, understand that to be certain kinds of vibrations over the category of finite sets, and understand operads to also be certain kinds of some like vibrations over the same thing, and then express this. I think maybe it's related to clubs, but I've never actually learned what a club was really. So
I mean, it's something over finite sets, symmetry maps. I think
maybe it is
read
exactly
read
that.
a special case where you got a vibration.
Yeah, that sounds very right. Um, yeah, and that's probably by far earlier than the paper I'm talking about, which is a infinity categories paper. Okay. So back to the double world. So what's the problem? If these two have equivalent notions of algebras, here we were doing categories. Remember that was the loose direction. What's the issue? Well, recall that what we're interested in is maps. One to this systems theory of graphs, right? So these are maps. And we now can see that they're maps. And before we were talking about them being collacs, but that is in the tight direction. In the loose direction, right? In the loose direction, they are actually, they just preserve everything. They don't have a loose. Well, I mean, you could make one out of the tight one, but there's nothing going on in the loose direction that we've talked about. However, if you did it with a double operad morphism, you would be forced to be loose in the, you're forced to be lax in the loose direction. So maybe I'll continue this later. I think I have to stop now.